Hi, today we're going to work out the example of the spherical oven, which I've drawn here. We have an oven consisting of several layers, namely a layer of bricks, a layer of stone, and a layer of metal. And we want to find the temperature T1 inside the oven if we know the temperature T4 outside the oven. So we know that for a spherical geometry, we have a general formula for the temperature, which is T equals minus K1 over R plus K2, with K1 and K2 being constants, and this R can be any arbitrary radius. So let's first look at this constant K1. We know that for the heat flow, phi q, we can write the heat flux times the area. And for a sphere, this area is equal to 4 pi times the radius squared. Please note that this area is not a constant for a spherical object. It depends on this radius r. If we now fill in the general formula for our heat flow, we can write this as minus the heat conductivity times the gradient of the temperature over the radius r times our area. If we now plug in this formula, our formula for T, we get minus the heat conductivity and then the gradient of minus K1 over R plus K2 times the area. If we rewrite this, we get that this equals to minus our heat conductivity times K1 over R squared times 4 pi R squared. And now we can see that this R squared cancels each other out, and we get that the heat flow is equal to minus the heat conductivity times 4 pi K1. And if we rewrite this again, we found that for K1, this is equal to the heat flow times the heat conductivity minus 4 pi, with a minus sign actually here. Okay, so now we have found an expression for K1. Let's now look back on the example, and we want to find this K2 value. So, for example, for the layer of metal, we already know that the outside temperature is T4. So let's look at this temperature T3, because eventually we want to find the inside temperature T1. So we can write for the temperature now, with this K1 value, that the temperature is equal to the heat flow times the conductivity times R plus K2. What we know is that the radius of R4, the temperature is equal to T4. So we can write R is R4 equals T4. So if we know this boundary condition, we can find our K2 value. Namely that K2 is equal to T4 minus the heat flow times the heat conductivity 4 pi R4. And if we look at this first layer, we can say that our T3 is equal to our heat flow with the heat conductivity of our metal layer times 4 pi. And then we first have our radius R3, and then from our K2 we have the radius of R4, and we have our temperature T4. If we fill in everything, we get, for the heat flow, the value of 1000. The heat conductivity of the metal is equal to 20 times 4 pi. And then the radius, which is equal to 0.25 minus 0.253 plus the initial temperature, 20 degrees. And this gives us 20.90 degrees Celsius for our T3. Try to find the temperature of T2 by using the exact same way, but then, of course, using the different radius. Try it yourself, and then we can look at it together. If you filled in the equation correctly, you find that for the temperature 2, we find 850.96 degrees. Let's now look at the last layer, namely the layer of bricks, to find our inside temperature T1. So, for T1, we can write again our formula. The brick times 4 pi r plus K2. And we again have our boundary condition that at T, R is R2. We know that our temperature is T2, which we just found. Then we can say again that our K2 must be equal to T2 minus the heat flow times the thermal conductivity of the layer of bricks times 4 pi R2. Okay, if we plug in this K2 in this formula, we find that our T1 is equal to the conductivity 4 pi, and then first our radius of 1, which you want to find here, and then the radius 2 from our K2, plus the temperature at 2. If we fill this in again, we find 1000 divided by 1 times 4 pi 0.15 minus 1 over 0.2 plus our T2 temperature. And this gives us a final temperature of 948.59 degrees Celsius. And this is our inside temperature T1. As you can see, it is quite high when you compare the outside temperatures only T4, but that of course is due to these very isolating layers around it.